Welcome to the deep dive. Today we're looking at something pretty fundamental, handedness, or chirality as it's properly called.
That's right.
And we're going to see how this simple idea connects, well, everything from our own bodies to the basic rules of the universe.
Exactly. Chirality comes from kheir, the Greek word for hand. The formal definition is being non-superposable on your mirror image.
Like my hands, right, left and right are mirror images, but I can't perfectly stack them.
Precisely. They're enantiomorphs. Or think of a screw thread. But something like a sphere. It's a chiral. Its reflection looks exactly the same.
Okay, simple geometry. But you're saying this matters deeply for life.
Oh, absolutely. Biology is incredibly specific about this. It shows what we call homochirality. Life effectively. Picked aside.
Picked aside, how so?
Well, nearly all proteins in life on Earth are built using only L-amino acids. That's the left-handed version. And DNA, RNA, they use D sugars, the right-handed ones.
Hang on, L for proteins, D for sugars.
Oh.
Was there a reason life chose those specific ones?
That is one of the great unknowns. It strongly suggests life had a single asymmetric origin, but why L and D, we don't really know for sure. It's a huge question.
Okay.
But here's where it really hits home for you, the listener. This chirality is critical for how drugs work.
Right, the left glove, right glove thing.
Exactly. Your body's receptors, enzymes, they're chiral too. So they might interact strongly with one enantiomer of a drug, the left-hand version, say making it therapeutic.
The other right-hand version.
Might be totally inactive. Or sometimes, unfortunately, it could even be harmful or toxic. It depends entirely on how it fits or doesn't fit with your body's own chiral molecules.
So biology is clearly handed. What about the universe itself? Does physics care about left and right? Let's maybe jump to Paul Dirac back in 1928. He was trying to square quantum mechanics with Einstein's special relativity, wasn't he?
Yes, a massive challenge. Dirac was looking for an equation that treated time on an equal footing with space. Mathematically, this pushed him towards using something called a four-component spinor for the electron's wave function.
A spinor? Sounds complex.
It is, but the amazing thing was, this mathematical structure he needed. It automatically explained the electron's intrinsic spin, its built-in angular momentum, something that before Dirac was just sort of tacked onto quantum theory.
Okay, so it explains spin. But didn't his equation also predict something weird, something unexpected?
It certainly did. Negative energy solutions, they popped right out of the math. Instead of just ignoring them, Dirac came up with this hole theory.
Holes.
Yeah, he proposed these weren't real negative energies, but absences, holes in a sea of negative energy electrons. And a hole would behave like a particle with positive charge. This led him to predict antimatter specifically, the anti-electron or positron.
Which was found just a few years later, right? 1932. Incredible.
It was. But for a long time, the assumption was still that the fundamental laws themselves didn't prefer left or right, that parity was conserved.
Parity conservation. So if you filmed an experiment, the mirror image version should follow the exact same physical laws, like flipping the film.
Precisely. Yeah. But then came 1957, and the Wu experiment. Jin-Sheng Wu and her collaborators looked at decaying cobalt-60 nuclei.
What did they find?
They cooled the nuclei way down and lined up their spins with a magnetic field. If parity was conserved, the electrons from the decay should have flown off equally in all directions relative to that spin.
But they didn't.
No, they didn't. Significantly more electrons were emitted opposite to the direction of the nuclear spin. It was undeniable proof.
Proof of what, exactly?
That the universe is fundamentally biased. The weak nuclear force, the one governing that decay, is maximally chiral. It violates parity completely.
Wow. So the weak force literally plays favorites.
It does. The theory demands it. We call it VA structure. It means the charge weak force, the W bosons, they only interact with left chiral particles. They completely ignore right chiral ones.
Only left chiral. But wait, how can particles even have mass then? Doesn't mass inherently link the left and right-handed versions of a particle?
You've hit the crux of the problem. Yes. A simple mass term in the equations. Mathematically, it connects the left chiral component, $, to the right chiral component.
But if the weak force only sees $, then adding mass like that would break the symmetry the weak force relies on. That can't be right.
Exactly. It would violate the fundamental gauge symmetry of the weak interaction. It was a huge theoretical hurdle.
And the solution is the Higgs.
The Higgs mechanism, yes, it's ingenious. The Higgs field permeates space, and particles get their mass not from a simple mass term, but through their interaction. They're coupling a Yukawa, coupling with this field.
And these Yukawa couplings they work differently.
They respect the underlying symmetry. The Higgs field essentially provides the necessary bridge, linking the left and right chiral sectors, is the particle's mass, but does so without violating that crucial weak force symmetry. The mass comes from the coupling strength times the background Higgs value, roughly 9Fa YFI trill 1 out.
Okay, let me try to summarize. Chirality, this basic handedness. It's not just in our hands or in life's molecules. It's baked into the fundamental forces, specifically the weak force, and the Higgs field is what lets particles have mass despite this built-in asymmetry.
You've got it. From hands to proteins to the very structure of particle interactions.
So what's the final takeaway, a provocative thought for our listeners?
Well, think about this. The charged weak force couples to left chiral particles. Now, because of deep symmetries relating particles and antiparticles, specifically charge conjugation and parity, this implies something profound.
Which is?
It must therefore couple to right chiral antiparticles. The antiparticle of a left chiral particle is right chiral. This rule is absolutely central to the Standard Model. And, just maybe this fundamental difference in how the weak force treats matter versus antimatter is a crucial clue to why our universe seems to be made almost entirely of matter today.
A universe built on a left-right bias. Fascinating stuff. That's all we have time for on this deep dive.